I am Professor Gora. Welcome to our academic playroom, where we look at how the world works through numbers. And I am Bondu, researcher. I've been out in the garden all morning, and I'm worried. We're looking at Sir Francis Galton's work from 1877. He took the largest, heaviest sweet pea seeds he could find and planted them, expecting the next generation to be even bigger giants. But the results don't make sense. I've been checking the weights, and the giant mother seeds produced babies that were consistently smaller than themselves. It looks like the experiment is going backward. If you start with giants, you should get bigger offspring. If that keeps happening, every generation should get taller and taller, right up into the clouds. Instead, they're getting shorter. Actually, the numbers show something very important. This isn't a mistake in the garden. It's a specific mathematical pattern. We call it the Great Regression. Look at Galton's results. Mother seeds are on the bottom, daughter seeds along the side. The line connecting them is surprisingly flat. If offspring matched their parents, it would be much steeper. Notice the clusters. Extreme parents produced babies huddled closer to the center line. Statisticians call this regression to the mean. It's nature's way of smoothing out extremes. When a trait gets very far away from the average, the next generation tends to move back toward the middle. So the giant seeds aren't shrinking because they're weak. They return to the average to maintain population stability. But what exactly is stopping them from getting bigger? Why don't we have peas the size of houses? Think of it like this. Here is a classic yo-yo attached to a thick rubber band. The hand holding the string is the mean, that safe, comfortable average right in the middle. When you throw the yo-yo down as hard as you can, that's like a giant parent seed, an extreme outlier pushing far from the center. The yo-yo can only go so far before the string pulls taut. It hits the bottom and then snaps right back up toward the hand. That's regression. It's like a mathematical safety feature, a rubber band that prevents the world from glitching out into infinite extremes. That explains the snapback, but why does the middle have so much pull in the first place? Galton realized a seed inherits traits from a huge network. He called this the ancestral unit square. Looking at the bottom half, immediate parents only account for half the genetic influence. Smaller boxes represent grandparents and great-grandparents. These ancestors act like a heavy anchor, pulling extreme offspring back to the baseline. It makes sense now. The combined weight of the plant's history is what keeps the new generation grounded. I see it now. The numbers weren't broken. They were showing us perfect, stabilizing balance. And it works both ways. Regression keeps giant peas from taking over the garden, but it also lifts exceptionally tiny seeds back up toward the safety of the middle. Galton's work provided the foundation for measuring these relationships today. He found the mathematical logic behind nature's balance. Math is like a kind gardener. It makes sure that even the most extreme outliers eventually find their way back home. Regression to the mean is the invisible geometry that keeps our world together. Now let's go get some pudding.